Okay, hello everyone. Good morning. I'm not a new face. I just unfortunately missed the last few days. Uh, Nice seeing you all. I'm Shravan. So today we'll start the session with Anna Christian Davis on screening fifth forces, a two-field example.
Okay, thank you, Sharon. I'd like to thank the organisers for inviting me. When I was thinking about what to talk about, I kind of wasn't entirely sure and thought, well, there must be a reason why I've been invited. So what do I do? Well, I have done quite a lot of work on modified gravity theories and screening. So here's the talk. And what I'm going to do is, first of all, review an introduction to these theories and some examples. And then I'm going to talk about a model that we have that's unpublished and is definitely based on a quantum gravity theory, sort of. It's based on a sort of axion-dilaton model that would be a remnant of string theory compactified to 4 dimensions. So I'm not entirely a fraud. So here's the outline. I'll talk quite a bit about chameleon models. That should be symmetrons, not symmetries. And I'll talk a little bit about the runaway dilaton before heading on to the axion-dilaton model, which is work done with Philippe Brax, Cliff Burgess, Carsten van der Broek, and Adam Smith. I'd like to highlight Adam, who's a first-year PhD student and is amazing. So this is a sort of follow-up from the paper that appeared yesterday that also involves Adam and included Maria Maklova. Well, why modified gravity? Well, what are they first? These are theories which modify Einstein theory, but reduce to general relativity in a certain limit, in the same way that general relativity reduces to Newtonian gravity in low velocities. One of the original motivations was that we saw the universe was undergoing an accelerated expansion, and there were a lot of talk on scalar potentials giving rise to an accelerated expansion, and looking at a modified gravity theory was a natural extension of that. Another reason is that you are testing general relativity in regimes that it hadn't previously been tested in, with a lot of lab experiments. Hey, tech, I can do that. So here's the microwave background. We've got this is the Planck results. We've got the hot spots, the cold spots. The galaxy has been taken out of this. And this is just beautiful. It gives the CMB predictions with tiny weeny error bars. It's quite amazing. Unfortunately, it didn't produce anything new that we hadn't seen in the previous experiments. You know, you might hope for hints of new physics in the CMB. They're not there. But we have this very confusing picture of the universe when we fit our cosmological data, the CMB, large-scale structure, everything we know and collect. We realize that the universe we know and love, that the matter we know and love, is just 4%. That's the quarks, leptons, photons, tables, chairs, people. We have 20-odd% dark matter. We know this is there. We've known for a very long time about dark matter from galactic rotation curves, from the bullet cluster, and we've got a lot of dark matter in the galactic halo. So what dark matter is, we don't know. But there's something even more mysterious, dark energy, which makes up most of the energy density of the universe. And it's funny because for a long time, we knew the universe was flat. And we knew the parameters we had did not make it flat. And then the supernova results came along in the late 20th century and said, oh, the universe is accelerating. We've dubbed all these things we don't understand, dark matter, dark energy, as dark. That's because they're not luminous. They don't interact with photons. But we can determine their energy density. So the universe is undergoing this accelerated expansion. It could be a cosmological constant. If so, it's 120 orders of magnitude below the natural value. You put in the cosmological constant into Einstein equations, and you would expect it to be of order the Planck scale. It's not. The lowest scale it could be could perhaps be the supersymmetry breaking scale, whatever that is. It's not. It's titchy. It's tiny. But it could be the dynamics of a light scalar field. The mass of the scalar field has to be less than the Hubble constant today, has to be around 10 to the minus 33 eV, which is again a tiny weeny mass. So, you know, it's still a mystery. If it's a scalar field, then if it's coupled to gravity at all, it will give rise to an extra force of gravitational strength, and we don't see that. As I said on Monday in the panel discussions, I sort of suspect that this is giving us a hint of we're treating gravity and quantum theory incorrectly, and there's something else there. But we do the best we can at the moment, and this is the best I can do. So why do I say it could be the dynamics of a scalar field? The energy density of a scalar field is the kinetic term, half rho dot squared, plus potential. The pressure is a half rho dot squared minus the potential. So if the potential dominates over the kinetic energy, then it's got an equation of state where the pressure is approximately minus the energy density. And if that's got the equation of state, it will give rise to an acceleration of the universe today. So the scalar field could play the role of an effective cosmological constant. And this is the Rathrup-Peebles potential. It's a 1/5 potential. The scalar field is rolling down the potential. And if it reaches large values today, here, this little thing here between the 0 and whatever it is, could give rise to the accelerated expansion. If that's the case, then we either have to keep it completely decoupled from matter by some symmetry principle that we have yet to discover, or we have to figure out why we don't see a fifth force. We parameterize deviations from Newton's law, but this is the Newton potential minus G Newton over R. We parameterize deviations as 2 beta squared e to the minus R over scale factor, or mass of the scalar particle. And the tightest constraint on this parameter comes from the Cassini satellite. Here's Cassini well, Cassini is dead now, of course. It was there looking at the rings of Saturn, sending radio waves back to Earth, and these were deflected around the sun. And some relativists, I think in Rome, but forgive me for forgetting the names, looked at the way how the radio waves were sent and received, and managed to constrain beta squared to be less than 4 times 10 to the minus 5, which is pretty strong constraint. So if we were to shove that in, then this thing would hardly do anything. You get a similar constraint from lunar ranging. The Apollo astronauts put mirrors on the moon, 3 of them. And the idea was to have a very strong laser and measure the Earth-Moon distance. And in doing that, you can also measure deviations from relativity, and you get a very comparable constraint. So if there's a fifth force, it has to be screened in the solar system. There are 2 very general classes of theory. One has a chameleon type screening, and this is what I'm going to be talking about. You can test this in the lab, in the solar system, astrophysically and cosmologically, and it does not affect the speed of gravitational waves. So it predicts that gravitational waves travel at the speed of light. There's also Weinstein screening. This appears in a general class of Horndeski theories, where you have a very non-trivial kinetic term with higher order derivatives, but the equations of motion are all second order, order by order. And in Horndeski, it goes up to the 5th order terms. It's quite miraculous. I don't know how Horndeski came up with it. Well, I sort of do, because he said, but I still don't know. This contains Galileons, massive gravity camouflage. Here, there's a Weinstein radius, which is huge, and inside the Weinstein radius, the nonlinear effects are essentially switched off. Essentially, the Weinstein radius screens the nonlinear effects, and beyond the Weinstein radius, you pick up the modifications that the theory will predict. In general classes of Horndeski theories, the speed of gravitational waves is different from that of photons. They were originally constrained by the pulsar constraints, which gives very comparable constraints to that of the LIGO-Virgo event of neutron stars. But of course, this is a very clean constraint, and pulsars are astrophysical. So whatever we do with this, we have to ensure, if we do Weinstein screening, that the model we have, the speed of gravitational waves, is the same as that of light. So what is the chameleon mechanism? Well, this was originally put forward by Justin Curry and Amanda Veltman, and the cosmology was worked out in this paper here. Philip Brax, Carsten van der Broek, Justin, Amanda, myself. So we have the action with the Einstein-Hilbert term, a scalar field, a potential, and the matter particles. I've written this in Einstein frame. That is to say, the Ricci scalar is just there with no scalar-dependent term in front of it. But matter is moving in the Jordan frame and depends on the scalar field. through this coupling parameter A. If you sit down and write out the equations of motion, you pick up terms coming from here, and you can rewrite this as an effective potential containing the bare potential and the coupling term A, and in the matter era, the trace of the energy momentum tensor. So if we have something like the Rashomon-Peebles potential and a coupling function that increases with phi, so coupling A of phi would be e to the beta phi over m Planck, then this coupling is density dependent because of the trace of the energy momentum tensor in the matter era. So this effective potential has a minimum, and this minimum is density dependent. I stole this slide from one of my former research students, Camilla Shelby. So we have the large density, the minimum of the effective potential is at high, well, it's all this way up here, which gives the mass of the particle as being heavy. Low density, much lower. The mass is much smaller. So the chameleon changes color. Now you might think, great, we've done it. That's not all. You have to check what happens inside a heavy body. Let me call this body the sun or the moon. You compute your value of the scalar field inside the body of radius r. You compute it outside. And if it changes from the interior solution to the exterior solution in a thin shell at the surface of the body, then your fifth force is screened in the solar system. Essentially, the fifth force depends on the gradient of the scalar field, which depends on delta r over r. And if this is less than 5 Newton, the Newton potential of the body, then you don't see the fifth force. It's not enough to have it less than order 1. So here we've got it, the exterior solution, the interior solution, steeply changing in this thin shell. And the fifth force is completely screened. But if it looks like this, it's unscreened. So there we have a Madagascan chameleon. And for the 1/5 potential, there's various lab constraints. If this is the dark energy scale, then atomic interferometry say that the region up here is excluded. Torsion balance, the Edwash experiment. These are Casimir constraints and muonium. And this is potentially from the anomalous G-2. You mean this one?
So what you want this screening radius? You want that to be the radius of the solar system?
Well, you look at individual bodies. So you test it. I mean, in the paper with Brax et al., it was tested against the sun, the moon, all the bodies of the solar system. It's not the whole solar system, it's the individual bodies. Because but what you're doing, so if this is the sun, then out here, the chameleon's tiny. With Weinstein, you would test it for the whole solar system. And the whole solar system is inside the Weinstein radius of the sun or the Earth.
Don't you want to don't you want to screen the fifth force to be screened for the galaxy? So
Sure.
location.
Yes, you can. Yes, you can check that too. So you do it individually, but don't forget the galaxy is less dense than, say, the moon. So if you can screen the moon, you can screen the galaxy. But yes, you do check that. Of course you do.
This is I thought it would be the other way. So you say if you screen the moon, you screen the galaxy. I mean,
I believe that except for perhaps dwarf galaxies. But most galaxies, you can check it. I mean, you know, you sit down and you do the calculation, you do it once.
one force to be unscreened on cosmological scale.
Yes.
Right. So
And screened in the solar system to evade all fifth forces.
you say screen in the solar system, first screen the galaxy.
Yeah.
Right. The question will be the following. So, do you see that? Do you expect that the gravity should be, in some sense, screen decreased only in solar system or in other star systems as well?
Oh yes. You give me the object. I need its radius and its density, and we can calculate whether or not it's screened. So one potential test a former student of mine, Jeremy Sackstein, thought about was looking to see whether you could test chameleon theories if you take a cosmological void and there's a dwarf galaxy, find a dwarf galaxy in an essential void, whether you can test it there, because the dwarf galaxy, well, might not be screened depending on its size. There was an experimentalist who was going to hunt for dwarf galaxies in voids, but I don't think he ever did. So this has come out of symmetrons, not symmetries. Another model that Justin Curry and Kurt Hinterblicker came up with was the symmetron with a Higgs potential and a coupling function. What happens is that this is a symmetry breaking potential, and at high density, the field is sitting in the symmetric phase of the potential. At low densities, the symmetry is broken. There's a critical density. And so essentially you're switching off the coupling to matter, depending on the density. I'm going to skip that one. A model that I thought was really cool, I saw in a paper of Gasparini, Piazza, and Veneziano, which this is not quite what they had, but it's essentially a runaway dilaton from string theory. The essence of the potential is e to the minus alpha phi. And they had the dilaton as a quintessence field. It's a great paper, but it's not the easiest paper to read. With Damore, I think it's Damore, Piazza, and Veneziano, they realized that you could get equivalence principles violations because the dilaton field couples to everything. If you go from string theory, you have the dilaton, it couples to all the matter fields. Therefore, you get fifth forces. And they put constraints on this. Well, they showed that it was not viable because of the equivalent principle violation. I tried to get this to work in a runaway dilaton model. This is where I'm going to show myself up. In the strong coupling limit of string theory, the dilaton potential is a runaway potential e to the minus alpha phi. In the weak coupling limit of string theory, you can calculate the dilaton coupling to matter, e to the beta phi. And alpha and beta are actually known numbers in string theory, I believe. And you might think this is great. So this is a sort of artist sketch. Here's the exponential potential. Here's the exponential coupling. The effective potential has a nice minimum that will be density dependent. If you're a string theorist, you'll probably worry that this is only valid in the string coupling limit. So as phi gets big, we go outside the string coupling limit. And this is only valid in the weak coupling limit. So you're going outside. But the biggest worry for me is that when you sit down and compute the thin shell, you find you don't have a thin shell, you have a thick shell. So the fifth force is not screened. And I put this to one side. Instead, we realized that you can realize this with an environmentally dependent dilaton, where the coupling has a minimum. This is coming from Damour and Polyakov. I don't quite know why they had this form of, I've forgotten why they've got this form of coupling, but you get an environmentally dependent dilaton, and you can compute this. It gives nice behavior. It is a screened model. But it's still, well, but recently with Cliff Burgess and Adam, we came up with a new model. The dilaton does not arise in string theory all by itself. String theory starts supersymmetrically. And in supersymmetry, particles are in supermultiplets. The scalar multiplet is a scalar field plus a pseudoscalar. The dilaton field and an axion field. And this is not the QCD axion. And I must say, I was kicking myself when I realized that, because I should have known it when we did the environmentally dependent dilaton. Anyway, the axion-dilaton model has two kinetic terms, two derivative terms. It's competing with general relativity as the simplest two derivative theory. We can write the kinetic term as a metric, Gij, d mu phi I, d mu phi j. And because this is coming from a superfield, it's the metric we can take as a moduli space metric, d phi squared, w of phi, dA squared. A is the axion pseudo-scalar particle. Phi is the dilaton of scalar particle.
Well, usually the axion is created as a particle coupled to electromagnetic field in a certain context, coupled to the second invariant. Do you suggest here some coupling to electromagnetic field?
I'll come to the coupling to matter. Yes, of course. And I'll mention that right at the end. I mean, it's what we haven't done is to look at the coupling to FF dual. But of course you can put that in. And I must say it's something I thought one could perhaps test. So the scalar action would be Ricci, kinetic term for the dilaton, the coupling function between the dilaton and the axion, and the potential of the dilaton and the axion. And of course, there's matter action, which I seem to have neglected to write down. So the axion potential is assumed to have a minimum. And where the potential is 0, and this V of phi has an exponentially decaying potential, and it can have some phi dependent term as well. So when lambda is less than √2, this gives rise to a late time acceleration if we sit down and compute it.
Shouldn't that be the e to phi in front of everything? Typically, there is this e to phi that covers exactly the dilaton to everything that one has from.
You want my matter you want my action in, don't you?
Just asking.
Yes, there should be I haven't put the matter action in.
This is Einstein frame.
Ah,
Yeah,
okay.
this is oh, thank you. Yes, Einstein frame. Yeah, sorry. I don't like Jordan frame. So what we've got here is the dilaton influencing the axion and vice versa, which is very important. So the effective potential of the dilaton, I've written this down, effective potential of the axion has a form that depends on the matter that the axion couples to. And here I've got the dilaton coupling. I haven't put the matter action in, but that's what you're querying, I think. So this is motivated by the axion-dilaton system, which emerges from the volume modulus compactification from 10D to 4D. So the key ingredients is the influence of the axion and dilaton through the W coupling. The axion potential is taken to be phi minus A plus, which is a fixed point. And when it goes towards A plus, of course, it's 0. And coupling to matter and electrons. So the axion mass, when you sit down and compute it from the action, from the Euler-Lagrange equations, become density dependent, which is great. What I am not giving you all the details because they're, yep. This one.
Where does this come
from?
This is the coupling of the axion to regular matter.
This is the coupling to the electron, yes. This is coming from previous work on the axion-dilaton system. And it's because to implement a complete model with a screened fifth force, you're needing a fixed point. So I wasn't involved in the previous work, so I don't know the precise details. Here it's this is what it is, rather than I can derive it. Some things I could derive if I had enough time. So what's happening is that in a heavy body, like the sun, the axion is massive. And outside the heavy body, it's very light. And when you take these equations and compute what actually happens, the transition is happening in a very narrow region. So when you're feeding this in to the dilaton equations, you can take it as a theta function of the interior and the exterior solution. And then feeding this back into the dilaton equation, this coupling to matter, beta, depends on the axion field in the body. So sit down and compute what beta is. And it's very small compared to the bare coupling. So you can take your bare coupling to be whatever it is, but in the body, it's very small. So in the solar system, the dilaton field has a very small coupling. So you're screening the fifth forces. In a model that Philip Bracks, Cliff Burgess and Fernando Quevedo had, which predates this, they actually had beta going to 0, but they didn't really have any dynamics. So we've got the two coupled fields, and the dynamics of each field influences the other. With the axion switching from a value inside a body to outside, and giving rise to a very small dilaton coupling. I should say the dilaton is playing the role of the cosmological constant by its behavior of its potential, the runaway potential. We're avoiding fifth forces and passing these solar system tests. We can take specific examples, take the the coupling function between the dilaton and the axion as e to the minus phi over 2 lambda. I realize I've used lambda twice, and a dilaton potential of this form. So it's got a u of phi factor and the exponential factor. And then what Adam Smith did is he put it into class and computed the dynamics. So this is the background evolution. We've got evolution of the only thing we've assumed is cold dark matter. So we've got the dilaton potential. We've got the CDM. We've got baryons, radiation, axion fields in there. And the behavior of omega from all the different fields. So the axion mass I've got here, couplings, scalar parameter, and we've taken the difference A plus A minus as 10 to the 6th Jev. There's a few other examples, but this is the one I'm displaying. And you can compute the power spectrum. And compare it with lambda CDM. And we're doing a pretty damn good fit there. So that's the CMB, and this is the power spectrum, P of K. Well, it's not bad. Well, actually, it's pretty damn good. I can't justify where the parameters come from. They are parameters of the model. So what next? Well, there's various things we should do. One question that you asked was, what about coupling to electromagnetism? Well, I thought, actually a couple of days ago, that we can test this against solar physics. I suspect it will pass the tests because of the axion mass. But if you, I'm sorry, I've forgotten your name, but the axion couples to electromagnetism. So it couples to E dot B. In the very core of the sun, it will be too massive. But in the tachyocline, which is less dense, and that's at 0.7 solar radii, it will be fairly dense, but not completely massive. The magnetic field in the tachyocline is 50 Tesla. I don't know what happens, but we could compute it. And the reason we can compute it is because I've been there before in looking at chameleon production from the sun. I suspect that the axion field is going to be too heavy, and it won't. There'll be no constraints, but it's worth doing. We could go back to a lab test as well for the dilaton. I don't know what would happen. We haven't done it. But let's go on to our conclusions. So this is actually things that I have just thought about. The paper, the work I'm displaying is unpublished. So, you know, not done yet. So I presented you with the screen modified gravity model and briefly discussed the string dilaton as a modified gravity model. What I want to do next is to take that runaway dilaton model with the exponentially increasing coupling and the axion and see if it could work. I'm kicking myself for having neglected the axion. But, you know, to actually, rather than this fancy model, do something slightly simpler. I don't know, I suspect it won't work, but I've introduced an axion-dilaton model, which is definitely motivated by theories in extra dimensions. And we've analysed the dynamics with the dilaton behaving as the dark energy particle with a model with screening. One thing that you ought to be asking is what happens to dark matter. When we did the analysis in class, we put CDM in. Is the axion dark matter? I don't know. But this is in progress. So I think I'll stop there.
It's perfect in time. So
Could you tell us a little bit about that you used terms dilaton and axion? It's not clear to me the extent to which this really is similar to the dilaton axion system in, for example, type 2b supergravity, because that actually has an SL2 symmetry, which when you write your potentials down, that's broken. So I guess the question is where, I mean, I don't mind you using the words axion and dilaton because you also had the word motivated in there, which is fine. But can one see a little bit, where are these potentials coming from, supposed to be?
So, gosh, so you're querying this, aren't you?
And a system with an SL2 over U1 symmetry has kinetic terms with all sorts of nonlinear structure in it,
Yes,
but doesn't have potentials because the nonlinear realization actually pushes these fields around, and potentials don't do that. Right. So the derivative terms can have that symmetry, but the potential, unless there's a mechanism that I haven't right now, still a bit sleepy, haven't thought of, but they're coupling to form fields and other things around the supergravity model. So it depends. You may be implicitly turning on a whole bunch of other stuff, which I don't know what it is.
You might be implicitly turning on a whole bunch of other stuff, but I'm not entirely sure about that. So this potential you can find in the Bible called Green, Schwarz, and Witten.
Okay.
Well, if I can find it in the Bible, I'm sure you can.
Mm-hmm.
No, seriously, in the strong coupling limit, you do get an exponential potential for the dilaton. So I don't think that should be queried. In the same way that you can get the coupling parameter, the exponential coupling from Green, Schwarz, and Witten.
Mm. Okay.
Or you can ask Michael Green, that's easier. It could be there, I don't know. The specific form where we used, well, actually what we've done in practice, we've got 4 different examples that went into class with and without this thing and different coupling functions. And I've picked the one that works best. It might not be the simplest one. This particular form of V is coming from a paper of Burgess and Quevedo. It's their yoga potential, where you're relaxing. I don't know why people think that you relax in yoga. I should take them to an Ashtanga class, but Cliff thinks you do. It's coming from their yoga potential there. So we just took that. We took this as one of our examples. You are quite right. If I were to go down and do SL2 compactification, I'm not sure what I would get. Well, actually, I wouldn't get very much because I probably couldn't do it. But so you can treat this as a axion-dilaton phenomenology motivated from the original super multiplet containing the dilaton and the axion. And I put a little bit of string theory in because every so often I think that I ought to be able to derive a screen model from string theory. But since I'm not a string theorist, I never get very far. Perhaps you should help me.
No questions.
Towards the beginning, you mentioned that the quintessence field should be quite light, very light, extremely light, actually 10 to the minus 13 electron volt, if I remember correctly. My question is whether in some of these models, you can have such very light field natural. Maybe with this string theory embedding or some symmetry. What do you think?
If you have a very light field, it's looking like a pseudo Goldstone boson. If you say which the compactification of string theory is, I think we could sit down and calculate it. But since we don't know yet how to get the standard model out of string theory, I don't know. I think this is what you're referring to, isn't it?
Yep.
Yeah. I think.
Yeah, I have a comment on this, on your point. So in string theory, if you can get, to my surprise, you can get naturally small masses if you give yourself the freedom to tune the string coupling constant. And it's a logarithmic tuning of the string coupling constant, which leads to order 1 change of the mass. So you don't need exponential tuning of the string coupling constant to get small masses. And I can give you the reference for it.
Yeah, whether the actual mass immediately comes out, I wouldn't know. But we're still trying to get the standard model out of string theory, I believe. I'm told we're down to 100 Calabi hours now from Kelly, rather than however many it was originally.
Well, the question which I would like to ask to many other persons who work with cosmology, in one expression, use the potential with negative degree of phi. So the problem is, but we usually assume that this phi is small. That is one lambda. Yeah, just this retrapibbles, but. We should have very hard difficulties if this phi will be small. How we deal with this problem?
This quite clearly is not. You quite clearly can't have a fundamental model with just a scalar coupling and this potential. It has to come from somewhere else. So the somewhere else would have to give some form of physical cutoff. It's an effective potential. It's a potential that gives you the idea that, at large values, you could be a cosmological constant, an effective cosmological constant. And, do we really query Jim Peebles? No, I mean, I think it's, you can't say this is a complete model. In the same way that we might think that the standard model of QCD and electroweak is complete. We might think that. It probably isn't, but it could be.
Since you have the slider, I want to investigate a bit further. So you have this exponential. So there's this parameter lambda, and you say that it's constrained, Cassini constrains the beta squared, but I guess that depends on what scale you put in, right? So
It does.
Could you give some more details?
I haven't displayed all there are various plots of the constraints on this Yukawa potential as a function of the Yukawa mass or scale and distance and coupling, but no, I haven't. Sorry, I haven't got that plot. It does exist.
Any more questions? If there is time, I have a question. Any effects of fifth force towards the galactic centers? In the galactic center, maybe around supermassive black holes or some distance from supermassive black hole.
It's funny you should ask that. You can try to look for that around the galactic center. As we know, the stars are orbiting quite close to the galactic center, and you can try to test the effect of a fifth force on the motion of the S stars. I mean, the thing is that the orbit, I think, is something like that. I think the closest one, the orbit's about 30 years. So you might need a while to test it. But yes, it's not a dumb question.
Okay, well, 30 years is not that long.
I could try to display another plot of that, but it's in a different talk.
Okay. Any further questions? If not, let's thank Anne again.